So here we have the 2018, this is question 8, paper 2, leaving cert higher levels. So firstly, Acme Confectionery launched a new bar called Chocolate Crunch. The weight of these bars are normally distributed, so they have a mean of 4.6 and a standard deviation of 0.12. And a sample of 10 bars select at random. So we have a sample of 10 and the weight of the sample is found. So you want this probability that the mean weight is between 4.7 and 4.6. So to do this, I'm going to have to get z values. So my formula for z values of the mean is x minus u over, and I have to put it over the square root of the sample size as well because it's the mean. So say if I want to, I'm going to first have to put in 4.6 and then 4.7. So 4.6 minus, so my actual mean was 4.64 here, so that should be 4.64 minus 4.64 over the standard deviation, which is 0.12, and then the square root of the sample size, which is the square root of 10. So I'm just going to plug this into my calculator. So 4.6 minus 4.64 over 0.12, and then I'm just going to put brackets 0.12 and then over the square root of 10. So I get is equal to minus 1.054, so 1.054, and now I'm going to plug in 4.7. So it'll be 4.7 minus 4.64 over 0.12 over the square root of 10. So I can literally just go back to my calculator but just plug in 4.7. So I'm just going to do that there. And then I get 1.5811. So I'm looking for the probability that z is between 1.5811 and minus 1.054. So my mean in the middle is 0, and then here somewhere it's going to be 1.58, and then this side is going to be minus 1.05. So to get the probability that it lies in between, first I'm going to get the probability that it's less than 1.58, then I'm going to get the probability that it's less than this one, and then take that away. So first, the probability that z is less than 1.58, so I'm going to go across to my tables. So 1.58 is 0.9429. And then the probability that z is less than minus 1.054. Well, I can't get less than of negative, but I can put the probability that z is greater than 1.054 because the curve is symmetrical. But I can only get something less than whatever, so it's going to be 1 minus the probability that z is less than 1.054. So the probability that z is less than 1.05, so 1.05 is going to be 1 minus 0.8531. So that's going to be 1 minus 0.8531. So I get 0.1469. So that's the probability that it's less than 1.58. So the probability that it's less than 1.58 is equal to 0.9429, and the probability that it's less than minus 1.054 is 0.1469. Well, then I can just subtract to get the probability that it's between. So 0.9429 take 0.1469. So 0.9429 take 0.1469, and then I get 0.796, and that is my probability that the weight is in between there. And then the next question, a company surveyed 400 people chosen from the population who bought at least one chocolate crunch bar. Of those surveyed, 324 of them said they like the new bar. Create a 95% confidence interval. So my standard, so I'm going to have to get my standard error of the interval. So my standard error can be got by p 1 minus p all over square root of the sample size. So if I want to get, so my sample was 400, and then the population proportion, which is p, is 324 over 400. So if I want to create a confidence interval, it'll be p minus 1.96 by the standard error, which is p 1 minus p over n, and then is greater than or equal to, is less than p, so p plus 1.96, and then the standard error 1 minus p over n. But I could also write that as p, the population proportion, plus or minus 1.96, and then p 1 minus p over n. So I might just leave it like that. So firstly, I'm going to have to get, so I'm going to have to fill in, say, this first. So so p is the population proportion. So this is really actually p hat. So p hat is 324 over 400, and n is 400. So this is going to be 1.96, and then so I might work that out. 324 over 400 gives me when I work this out, it gives me 0.81. So that's going to be 0.81, and then 1 minus p is going to be 1 minus 0.81. So I get 0.19, and then that's all over n, and n was 400. So I'm going to work out this. So 1.96, the square root of 0.81, and then 0.19, and then over 400. And then I get 0.03845. So so p I got was 324 over 400. So it's going to be p plus or minus this, so 0.81, and then plus or minus this. And it says correct to 2 decimal places, so I'll put 0.81 plus or minus 0. Correct to 2 decimal places, it'll be 0.04 corrected 2 decimal places, but we have it in there anyway. So the next part of that question is put a tick in just sort of looking at statements. So the first section is when forming confidence intervals for a fixed value of n, an increased confidence level implies a wider interval. So say if we have a 95% confidence interval that that our population lies between 2 and 10. That means 95% of the time our values are going to be between 2 and 10. But if we had a 50% confidence interval that it lied between 2 and 10, that means that 50% of the time it lies between 2 and 10. But that doesn't necessarily imply a wider interval. So say if we had, say, 50% of the time the values lie between a certain number, if we increase the level of our confidence level, it doesn't necessarily imply a wider interval. So I guess say if it could be sometimes true, say if we had 50% confidence interval, it lied between 10 and 12, and then we wanted to get a 95% confidence interval, so then the values will be, say, greater. So I guess this one could be sometimes true, but it doesn't necessarily imply, because 95% could actually be within the same interval, or so it doesn't necessarily, so I would say sometimes true. And then as the value of p increases for fixed n, so the estimated standard error. So as the value of estimated standard error of the population increases, so estimated standard error. So as the value of p, so p is the sample proportion. So if that increases, the estimated standard error of the population increases. So with this, our formula for the standard error is p 1 minus p. So this can only be like whatever p is, 1 minus p. So if p increases, well then it's going to be 1 minus whatever, they're going to be multiplied. So I would say that's not true. But then it says, as a value of p 1 minus p increases for the estimated the estimated standard error. Well, the standard error is equal to, it's directly proportional to p 1 minus p. So as that increases, the standard error would increase. So I would say yes. So as n, the number of people sampled increases, the estimated standard error of the population increases. Well, if we sample more people, they're inversely proportional, so the standard error is going to decrease. So I would say no. And then for the next part, it says, using calculus or otherwise, find the maximum value of, so p 1 minus p. So we want to differentiate this in terms of p hat. So this is p hat, what I would call it. So I'm going to first multiply it out. So p hat minus p hat squared. So if I want to differentiate this in terms of p, this is going to be 1 minus 2 p hat. But if I want to get the maximum value, I have to let it equal to 0. So equals 0. So 1 is equal to 2 p hat. So if I want to get p by itself, it's going to divide both sides by 2. So I'll get a half is equal to p. So that's the maximum. So say if p is a half, well then the maximum value of this will be a half by a half. So it's going to be a quarter. So that's our maximum value. And then it says, find the largest possible, so I think they mean range of the 95% confidence interval. So OP, so is P, so we're going to get this largest possible, say, error. So the largest possible value for what's above, we already got the largest possible value for P was a half. So then it's going to be a half by a half, which will be our above one, which will be a quarter, which is 0.25. So the square root of 0.25, and then they say for a given a sample of 800, so it'll be over the square root of over 800. So well, the largest range would be, say, so that's going to be our standard error. So it'll be 0.25 over 800. And then I get 0.0176. So that's, say, our standard error, but I'm not, they might mean that they actually want how far does it go on either side. Well, it'd be 1.96 by the standard error, which will be 1.96 by 0.25 over 800. Because for a 95% confidence interval, it goes 2 standard deviations from the mean. So the largest possible, it'll be whatever the sample proportion is plus or minus this. So 1.96 multiplied by this standard error is 0.0176. So 1.96 multiplied by 0.0176, and then I get, so it's the population proportion plus or minus 0.0345. So that's my answer for that. And then the next part, Acme Confectionery has an employee pension plan. For an employee who qualifies for a full pension, Acme Confectionery will pay a sum of 20,000 on the day of retirement. So, and pay a sum on the same date each subsequent year for the next 25 years. Each year, this employee is paid a sum that is 1% more than the amount paid in the previous year. What sum of money must the company have set aside in order to fund this pension? So, well, on the first day, he's getting 20,000, and they're saying assuming an AER of 2.4%, so money is growing at that percent. So I'm going to bring all the values back to the day he actually retires. So he retires on this day, he gets 20,000. Then he retires a year later, he gets 20,000 plus an extra 1.1%, so 1.01. But we have to bring everything back to this value because we want how much they'll have to pay at this point. So we have to divide by how much the money will have grown, which is 1.024, because our AER is 2.4%. And then the next year he's going to be paid whatever this was, and then plus another, multiplied by another 1.01. So I can write that as 1.01 squared, and the 1.024 will have been, we'll have to bring that back 2 years, so 1.024 squared. And then that'll say go on, and they say for 25 years, so 20,000, and then so each so they pay a sum on the same date each subsequent year. So they pay him one day and then for another 25 years, so 1.01 25, and then divided by 1.024 25. So now we can set up a geometric series where our first term, so we have our first term A is 20,000. Our ratio is 1.01 over 1.024, and the number of terms we have is 26 because we have to count the first term, and he pays 25 years after that. So I'm going to set this up into my sum for a geometric series. So the sum of, so Sn is A 1 minus or n over 1 minus or. So it's going to be 20,000 1 minus or, which is 1.01 over 1.024, and that's going to be to the power of 26 because that's the number altogether is 26, and then 1 minus 1.01 over 1.024. So I'm just going to have to work this out on my calculator. So 20, so I'll just put a fraction, 20,000, and then multiplied by 1 minus, and then make sure to use brackets, 1.01 over 1.024, and then that's all to the power of 26, and then 1 minus 1.01 over 1.024, 1.024, and then that's, so I'm just going to check I have everything entered in correctly. So minus 1.01 over, so power 1 minus, and then 20,000. So that's okay for that. So altogether it's going to be 440,132.40. So that's how much they're going to have set aside on the day of their retirement. So that is our answer for that. Thank you.